So I thought I would do another example right here, a case where you have horizontal normal forces. All of our normal forces were either vertical or nearly vertical right here. So I said, well, suppose we have a block sitting on a smooth surface, so there's no friction here, and we give it a push. We keep this push going, and we have a block here, and we have friction here, and we want to know what's the smallest force I can push to keep this thing from falling right here. You notice everything is going to be accelerating to the right here. Okay, so how do we calculate this thing right here? Well, first thing is, let's say we are given the coefficient of static friction right here on that surface, and we're given the mass. This is m, and I'm going to assume that one is 10m right there. And what we want to do is we want to determine the minimum force, this P force, for M not to slide. If we push too easy, if we didn't push it at all, it would definitely just fall down right here. Okay. So we look at the forces on this. On this block right here, there's the P force right here. Since it's the hand force, it's really a normal force, but I have enough normal forces, so I'm just going to call it the P force. We have two other surfaces here, N2 and N1 right here. We also have 10 mg coming down, and we have a frictional force. This block is trying to pull the front end of this block down with the frictional force. The other block over here, we have the same normal. These are equal and opposite reaction forces. We have the mg, and we have the frictional force. Remember, for every friction, there's an equal and opposite friction on the other block right here. So here's all the forces. I put my coordinate system in. I'm going to call these directions positive. So now we can go ahead and write out the sum of the forces on each of these two blocks. So the sum of the forces in the x direction on the 10m block, we got the P going this way minus the N1. It is accelerating. They're both accelerating at the same value, equals 10ma. Don't forget, this is 10m right here. Some of the forces in the y on this block. We have N2 going up, we have the 10 mg coming down, and we have the friction coming down. And this block is not accelerating this way, so it equals 0. The smaller block, some of the forces in the x direction, we just have the N1, and that just equals ma. Again, the same a as that one. And the forces in the y, frictional force up minus mg down equals 0. This is static friction right here, and we're on the verge of slipping. Why? Because we said P is a minimum. If P is a minimum, then if I go any less, it would slip. So I must be on the verge of slipping. So when you're on the verge of slipping, it's not less than or equal to, it's equal to mu Sn. Okay, so now I have, these are my equations right here. So I said, okay, let's take my ma right there, which is N1, and just put it right there. So I'm just going to make that N1. So now we have P minus N1 equals 10 N1, or move that N1 over, and so we get P equals 11 N1. Now if we take this equation right here, the friction is equal to mg, and so friction, which is equal to mu s N1, is also equal to mg, so we can get N1. N1, throw the mu s down below. N1 is mg over mu s, and we'll just put that N1 right up into here. So that minimum force is 11 mg over mu s. And you can see if mu s were 0, this would be infinite. It would require an infinite amount of force to keep that from falling right here. The rougher this is, the rougher this surface is, the less I can push on this to keep it from falling down right here. Okay, so there's one case where we're accelerating in a straight line. But we can also do this for accelerating in a circle. So I'm just going to come down to the carnival ride, where you have a round room, and you have people sitting against the wall of the round room, and then they get this thing spinning real fast, and when everyone gets real sick, they drop the floor right here. Now, hopefully, you don't drop right here. Hopefully, you stay right there. One thing you don't want to do is throw up, because if you throw up, guess where it's coming? It's going to come right back and hit you. So don't throw up. Okay, so now what are the forces on this right here? Since we're going in a circle, we do want to put one axis toward the center of the circle. The other one, it doesn't matter, we'll call up positive. What do we have? We have a normal force. There's the surface pushing in on you. We have the friction keeping you from going down, and we have mg going downward right here. And this r is the radius of the circle. So if we look at the sum of the forces in the in direction, we just have our normal. That's it. There's our normal. It's the only one. And that equals, remember, when you're going in a circle, it's mv squared over r, circular motion right here. If we look at the forces in the y direction, we have the upward, which is the friction, minus the mg, 0. And we also know, since we're on the verge of slipping again, because if we're going any slower, I'm assuming, because what we want to find is the minimum speed to not slip. That is, how slow can they get this thing going? So we must be right on the verge of slipping right here. So if we solve from right here, we know friction is equal to mu Sn, since we're on the verge of slipping. And so V is V min now. And now if I just put that right up into here, we get mu Sn equals mg, putting that on the other side. And now I'm going to solve for my n, which is mg over mu s from right here, and take that n up into here, see right there. And so we got mg over mu s equals mv squared over r. Or you notice the m's drop out, and we can solve for v min. Throw the r up above and take the square root. So the minimum speed is the square root of gr over mu s right here. So the smoother this surface is, the faster this thing's got to go, so that that you don't slip. So if you ever want to know if this is a scary ride, feel how smooth that surface is. If that surface is smooth, then you know that it's going to be a pretty scary ride right here. I don't know if I'd get on there in your silk pajamas, because you might not sit there right there. So there's the minimum speed right there. Now, you notice it doesn't depend on the mass. The mass drops out, so the mass doesn't matter here, except it might matter later on, because if you had a whole bunch of heavy people on one side of this ride, it would be like the washing machine when it's in the spin cycle. If all the clothes get on one side, then the whole thing starts to shake right here. And that's up for a later chapter, but that's when the angular momentum, instead of pointing this way, it gets bent a little bit this way, and now as it goes around, it's going to kind of jiggle the whole thing right here. So, but that's for a later chapter right here. But this is the case where you have an inward acceleration when you're going in a circle. Here you got a horizontal acceleration, kind of doing the same thing. Okay, so hopefully this will help you with these type of problems on the homework. Okay.